Hello and welcome to the Technical Symposium. I'm Paul Green with Biogas TV. Today, we're pleased to hear from Paques on the new Paques BIOCYCLONE solid separator. Our presenter today is Timur Dunayev. Timur is the managing director and CEO of Paques US, where he leads the company's North American business. With more than 20 years of experience in the environmental engineering and process management, Timur brings deep experience in advanced treatment technologies, including anaerobic systems, anammox systems, and biogas desulfurization. Timur is currently pursuing a Doctor of Business Administration in Organizational Leadership at the Thomas Edison University, where his research focuses on servant leadership and its impact on employee health and well-being in environmental organizations. He also completed doctoral studies in engineering at Villanova and holds a master's degree in water resources and environmental engineering. He's also a powerful force and teacher of Brazilian Jiu-Jitsu and has a whole mess of boys at home, 3 soon to be 4. So we'll have time for questions at the end. This is recorded, will be up on biogas.tv shortly. Timur, it's great to see you and have you teach us about the Paques BIOCYCLONE today. The floor is yours.
Oh, so much better than teaching BJJ. Paul, always tremendous pleasure to be here. You and I have done a bunch of this, and it's always good time. I'm really excited to spend some time discussing this new advancement. I'm really hoping that there are going to be questions. We're also strategically placing it so people can hear it and then come over to our booth at ABC next week and see the model of the BIOCYCLONE and maybe go into a deeper conversations about it. So thank you for the platform. Thanks for the time, and I really appreciate it all the time, Paul. Before I dive deep into the specifics of the BIOCYCLONE, I would like to say how this technology came about. And I'm passionate about technology development, so it's important to know how the technologies come through. And sometimes it goes through, let's say, academic circles and then gets adapted into industry. This one was not the case. This one was based on the deep conversations we were having with the industry and hearing the issues associated with the grit and sand. The discussion started, let's say, from the sand-bedded dairies and anaerobic digestion around sand-bedded dairies, but has since expanded into many different things because grit is an issue in many digestion projects. For this topic specifically, we're going to narrow it down to biogas digestion, but honestly, the application for the technology is quite broad. So without further ado, let me jump in and let's start talking about the technology. Basically, and we will show the characterization and the discussion around it as it pertains to hydrocyclone. But as the name implies, obviously, we're using the same centrifugal forces, right? Fundamentally, the biggest advancement that is brought in by BIOCYCLONE is the ability to control the discharge of the solids on a continuous basis. So what that means is that you're able to accumulate solids, compact them, and then discharge them in a controlled fashion, using sort of the best of the two worlds. The centrifugal forces that are same in the hydrocyclone, but also, let's say, a controlled discharge that we usually see in conventional clarifiers. And all of that in one enclosed, well-controlled system, which is applicable and appropriate for the biogas systems. In a comparison, let's talk about it. So we remove solids by centrifugal motion, same as in the hydrocyclones. But if you're familiar with hydrocyclones, the reason why they're so small, usually, right, relatively small, is because you do not control the back pressure. The main driver is the delta P across the hydrocyclone, let's say anywhere from couple PSI up to 20 PSI, depending on the application and what you're trying to separate. And then the delta P across the pressure drop with that and the atmospheric pressure on the discharge side is what's driving it. And so when you go into higher flows or higher volumes, there is two risks associated with using hydrocyclones, even if it's, let's say, multiple of them in parallel, right? What happens is you do not have a controlled, you do not have the thickening function. You will be separating everything based on the difference in the specific gravity and the amount of force that is applied. But then you're also losing the Vs. What biocyclone and the specific operation and the way we figured out how to operate the bottom pressure control allows you to do is to thicker the solids that are being separated and minimize the loss of Vs, right? And this is what we're trying to avoid in our industry. We're trying to lose the Vs because that's where the biogas is coming. So the way it operates, both in hydrocyclone in a biocyclone, there is a tangential inlet that creates the spiral force on the inside. The force is what's causing the separation. And then the clarified liquid comes out of the top, and then the solids separated go to the bottom, right? So this is the picture how it works. There is no difference in the biocyclone. We have exactly the same flow path. There's a tangential inlet, separation within the system. The gravity force and centrifugal force forcing the high specific gravity solids towards the bottom, and clarified effluent comes out. And here is where the discharge valve discussion is the most important, right? Once you separate it, if you control the back pressure, you are able to allow the solids to accumulate within the system. What it does at the same time, it thickens the solids, right? Because gravity is continuing to work. And then when the time is right, and that is determined from application to application, you're able to discharge the solids in a measured fashion. And you can do it both continuously and batch-wise. And so depending on how much solids there are in the system, how much you're trying to remove, and how much time you have to thicken the stream, you're able to discharge in a controlled fashion. So this is it's a continuous process of clarification, but a batch-wise discharge of thickened solids. And most of the time, what we do, if we employ it for the preconditioning of the solids, we operate the system in what we call a dialysis mode, right? And what you see in front of you is a block flow diagram describing what we mean by the dialysis mode. The basic idea is that if you have a feed manure pit, where, for example, you introduce dilution water or recycle water, you're conditioning your solids to be able to pump them further on. And this could be a good spot for you to remove the solids, right? In which case, we try to apply 2 to 3 times the flow through the biocyclone. And that allows you to continuously remove solids without affecting your forward flow overall in the loop, right? And once the solids are removed, all you're trying to do is to remove the heavy grit without losing any VS, and then VS goes forward for anaerobic digestion. If that is not enough, and in some applications, a single pass biocyclone might not be enough, especially if there is a lot of solids, or if there is no opportunity to install it, you can also include the biocyclone on an anaerobic digester itself. In this case, I'm describing our version of anaerobic digestion, which is the CBD, which allows you to recirculate the contents of anaerobic digester. So the mixing pattern is a plug flow pattern from top to bottom, enhancing the gravitational settling of the solids. And you're able to pull from the bottom of the digester only the heavy solids, circulate it around biocyclone so you can target the solids that have the potential to accumulate within within the reactor, right? And if you've been in the industry for a while, you know that the grit is going to be accumulating on the bottom, right? And depending on what kind of grit you have and what kind of solids you can have multiple feet inside of the reactor, right? And this would allow you both pre-treat in a dialysis mode that I described in the slide before, and also keep your digester clean if there is more solid carryover on a continuous basis, effectively keeping your system operational. Obviously, we have case studies. Obviously, we have photos. So I want to show you a couple examples of how this works. Here is a BioCyclone installed on a dialysis mode on a manure pit in a dairy in South Dakota. This dairy used to be, I'll move forward. This dairy used to be sand bedded. They switched to fiber bedding, but the blow-in sand and the remaining sand in the system still had created a lot of operational issues. It's 15,000 milking cows, 4 digesters for the total volume of 9 million gallons. And the manure pit is where the solids were conditioned to, let's say, around 8% TS. And the sand accumulation required basically weekly shutdowns to clean out the manure pit and the fiber removal equipment, which basically cost the client over $1 million a year and the downtime associated with it. So this $1 million does not include the downtime calculation. This is just a direct cost to bring the vacuum trucks, stop the system, drain the system, vacuum the sand out, and move forward. After we installed the BioCyclone on the dialysis mode, the frequency of the cleaning went from once a week to, I think, eventually once in 2 months. And that was only done preventatively. So the payback was less than 5 months for the installation. And so what you see on the right is exactly what I'm talking about. Because of the very specific mode of operation, and our ability to control the thickening of the solids. What you see on the right is that the vast majority of the solids, over 95% of the solids, were basically just the grit with very minimal VS loss, which is obviously what we're trying to do. Selecting the proper recirculation pump is obviously very important. If you've ever tried to pump solids that have a lot of grit in them, you know that a lot of if you do not choose the pump properly, is going to get eaten through. This is on the left is the example of the valve that we use for the thickening and the controlled discharge, and the right photo is the tangential sand entry flow. And on the top you see. Let me see if the mouse can move. On the top, you see the overflow that just basically goes back into the manure pit. Flow rate was around 400 GPM, average inlet solid at 8.1%, average clarified output is 7.9, which seems like we didn't remove a lot of solids on the first look, right? The difference between 8.1 and 7.9 is not substantial. But in reality, what we were purging from the bottom had 40 to 60% solids, better than any centrifuge that you can imagine. And so that actually is a great indication that the system was selectively removing heavy grit without affecting the forward flow and not losing any VS. And as I said, over 95% retention of VSS was occurring in the system. And that way, especially in the beginning, while we were processing the vast majority of the bulk of the sand, we were processing approximately 1 ton of sand per day. And so before, there was 6 to 8 feet of accumulation in the feed pit, fiber separation equipment plugging, and each descending, as I said, took downtime and cleanup time. We reduced it, effectively creating less than 1 year ROI. And the client is very satisfied. And in fact, we're putting another system for the same client in another location. They're available to talk. It's just, we didn't want to mention specific names in this. So here is an example. Here is the inlet manure fit, right? I'm going to play the video, see if it plays. Paul, let me know if it doesn't play. But basically, you see the 8% solids manure coming in into the pit through a coarse screen. This is the biocyclone installed next to the system, basically pulling from this pit and returning basically to the same pit. Right around here is the return line from the biocyclone. Um, Same video, sorry. And this is a control discharge of the solids that you can see. I'm actually going to pause. You will see the solids dropping. There is a tiny amount of water on the top, and that's literally less than an inch of any VSS on the top. Everything else is this coarse solids that you see settling. So basically, the entire hopper ends up being heavy grit solids. You can see them falling down, very thick control discharge of thickened solids in the operation. This is the quality that you see of the solids of the discharge, and you can see both larger solids, and obviously we have empirical data that is available on this particle size distribution and characterization of the solids, but you see both larger particles and much, much finer compacted particles as well being removed from the system. That's basically the case study and the presentation that we have. So
Good stuff. So there's our context. So Timur, the product is obviously new. Where do you see things going as far as custom sizing versus standard options? Has POC arrived at, say, any standard diameters, standard heights?
we've standardized on 4 different sizes right now, and we have seen the vast majority of the projects that we've evaluated to date fall in those between those 4 sizes, and the sizes are basically from a 5-footer to an 8-footer for the biocyclone diameter, which takes care of anywhere from, let's say, the low end of 300 to 400 GPM all the way into 2000 GPM, and that takes care of, let's say, a vast majority of dairies with more than 4,000, 5,000 cows, which is basically where we see anaerobic digestion projects as well.
So again, you said 5 to 8 foot diameter. How much does the height vary as projects change in size?
The height variance is not that much. It's right around 15 foot. The biggest thing to solve on site is where do the solids going to go? Are you going to be installing a hopper? Some clients prefer, we have a project that goes in, there's a retaining wall and a rail, and you install a biocyclone, and basically the solids are falling down on the concrete with a little bit of drainage so the front loader can take care of it. The system is very versatile from that perspective. And what's important is you can stack them multiple in a row, obviously, like the other hydrocyclone, except you don't need as many.
Right. Okay. Michael asks, does it work with gravel or just sand?
As long as it's pumping, and we need to evaluate the size of the gravel. With the gravel, we need to be able to see if it's pumpable, transferable, and if the equipment is properly sized. But it should be able to remove everything above 1 millimeter is going to be effectively removed.
How about abrasion? I'm sure POC has looked through this whole flow scenario at Achilles heel, potential for abrasion in either pipe elbows or rotating equipment. How thoroughly have you gone through the whole abrasion question?
Yeah, excellent question. Abrasion was on the front of our mind. Indeed, the pump selection and the proper material selection is the know-how here. Pumps do need to be properly selected and piping properly selected. We have checked the thickness both on the inlet and on the cone, And with the properly selected materials, after 1 year of operation, we did not detect any difference in the thickness. So properly selected construction material defend you from the substantial cost of the abrasion, but you do need to think about it in the engineering phase, without a doubt.
Can we just tab up to the slide on the CBD reactor? I just want to make a point of clarification on that real quick while we're together. So the collection at the bottom, just so people can take away and know what this is, the hydraulic rake drive doesn't really come across super clear by this graphic. So the POC, this CBD reactor, you've incorporated the biocyclone as a way to separate solids, but you're also separating solids on the tank bottom. Can you just describe that collection mechanism?
Yes, and the basic idea is to have some sort of collection mechanism on the bottom. The standard CBD comes with the holes precast in the concrete and a rake mechanism that is installed on the bottom of the reactor that continuously directs the heavy solids into the precast holes. And the entirety of the system drive and everything for the drive of the system are always located on the outside of the reactor. We never put anything on the inside because you need to be able to service it. If the solids are not that heavy, we can also just simply have, let's say, a collection of pipes that collect the solids from the bottom. And that is evaluated in between of how much solids you have and how much heavy solids you need to be removing from the system. So the standard application is a rake drive on the bottom, very similar to the rake of a clarifier that people are very familiar with, slow turning, robust construction materials, inverted gearbox that is fully isolated from the inside of the digester and fully operational and serviceable from the outside without have to stop the digester itself.
So pretty radical stuff, right? The industry has never really spent a lot of time putting rake drives at the bottom of digesters just for fear of it just ceasing and clogging up with solids. So that approach is pretty exciting.
Yeah, and while Biocyclone is getting rolled out in the last, let's say, year and a half, CBD has been in operations in full-scale facilities for over 5 years at this point. I think the longest installation is 7 years, and we have installation based in Europe, Brazil, China. So everything is available for the full. We have the full scale. This is a well-developed technology from that perspective.
So back to the biocyclone, how about fines? We talked about gravel, so kind of going on the coarse side of the solid spectrum. What about on the ultra-fine side of the spectrum? How does it deal with fines?
Fines need to be finely defined. And
finally define your fines.
Finally define your fines. So there is two things that I would like to mention. Without a doubt, smaller, less than 1 millimeter, and let's say 25 micron to 1 millimeter size is a little bit of a gray territory. There, obviously, a specific gravity driver has to become more. And the effectiveness of the separation is not that great compared to the larger particles, though we still observe, let's say, a cutoff depending on the specific gravity all the way down to 0.25, right? But I would ask the question also a little bit different. If the centrifugal force is not enough to separate those fines from the matrix of the liquid, is it actually an issue for the digester? Because those smaller fines, if they stay in the matrix, then they're not going to precipitate inside of the digester or sediment or settle, inside of the digester, and then they will come out with a digestate. And so I would say that even though the smallest of the fines are not separable, I would postulate that whatever is not separable by biocyclone is most probably not going to settle inside of the digester anyways, and will not pose the operational issues. It's going to stay bound into the matrix and removed with the digestate, like digestate comes out in.
Question came in, what is the maximum percent dry matter the feed can handle into the biocyclone?
We've tested 10 and above. The simple answer is if fluid is pumpable and the matrix is pumpable to the flows that we require, the biocyclone can take it. But in practical applications, we see that around 10% is where the cutoff is, right? Because above 10%, it's not a pumpable material in that sense, right? You'll need more like a dry hopper removal, and that's not the application for biocyclone.
Yeah. Well, a beautiful, simple, elegant design. That's right. Some of the best designs are elegant in their simplicity. So,
Without a doubt, I would be the first one to say that there is, as far as the mechanical parts, there's only two moving parts, right? It's the pump and the bottom valve. Everything else is static, and obviously the designed internals inside of the biocyclone are designed and installed in metal. The know-how is the proper selection of material, application, and the operations. So that's definitely where it's at. Otherwise, an extremely simple system, very easy to integrate, and especially for the dialysis mode, the integration does not stop anything in your day-to-day operations at all.
could you go to the slide? I think it's one after this. The question came in, what kind of conversion are you getting in MMBTU per milk or cow for typical sand-bedded dairy? So this site has 84 cubic feet per cow yield from the digesters. I'm thinking that hopefully answers your question. If we didn't, but in this
Yeah,
particular case, they're getting 84 cubic feet per cow for the digesters. Are we feeling like this may be typical or atypical, Timmer, for?
I think they were trending towards on the lower side because the HRT was getting hampered by the sand accumulation inside of the digesters. So it was falling behind 15, 16 days, which obviously is sort of the cutoff. But then after the sand got removed and the digester got cleaned out, the HRT was trending more towards the 20 days, and the biogas production was trending in the right direction.
So the desanding we're talking about here, that's the feed manure pit. These
Correct.
guys, are they still cleaning out their digesters periodically? How frequent is that?
I know that they had to clean out the digester before the biocyclone was implemented, right? Because there was years of accumulation. And so we don't have the data for post biocyclone because there's no cleaning right now or very infrequent. But before that, when they went in, there was more than 6 feet of
Yeah.
accumulation in under 5 years.
And so the answer to the 84 cubic feet per cow, that's per day, cubic feet per cow per day.
Yeah.
So the percent dry matter, does it affect the efficiency of separation?
Yes, for sure, because the viscosity is one of the main driving factors. Um, Obviously, percent ES affects the viscosity. Ideally, actually, using it on a digester is even slightly better in the configuration with the CBD, right? Because the VOCs get broken out, and actually the release happens, and the temperature is slightly higher. Um, Indeed, affects higher viscosity is slightly worse for the separation.
So what kind of reliability are we seeing for this South Dakota system? I
Once
guess
the
that would
pump,
mean percent uptime, or is there any downtime? Has it been
no,
down?
no, once the pump question got figured out, there has not been a downtime on purpose.
If you were to guess what might lead to downtime, let's say the pump or the separator just kind of sits there. The only moving part is the valve.
Yeah, only the pump.
Only the pump.
Once pump is if you have properly operational pump, there is nothing else that is going to lead to the downtime.
There
That is
is
within
some.
there is within our control. Obviously, a lightning strike is going to fry your electrical system, right? And so on and so forth. But what's within the engineer control, there's nothing besides the pump.
You've got some IP with the valve, but can you comment on the reliability of the valve? Because that's really intense duty, right? There's just a lot of sand pressing down
Yeah,
on the valve, and that would be a big wear part. How is that addressed as far as wear and tear on the valve?
proper selection of the equipment. And as I said, that's the entirety of the know-how.
Yeah.
Through very painful trial and error, selecting the proper parts. And we have standardized around couple specific valves and systems, and the drives and the controls and the pumps. And the combinations of those is what brings the mechanical reliability of the system.
Yeah. Well, good. We're out of the questions, and this simply, we certainly got the point across here of the biocyclone. So, in lieu of any additional questions, POC again is going to be at the Detroit conference next week. If you've got a project you just want an estimate on, reach out to POC. It's very simple these days to just get a quote out to you. I will send these slides out to all of you as soon as we get off the phone here. Of the phone, right? The phone. Yeah.
The phone.
But Timur, any parting remarks before we wrap it?
Always a huge pleasure, Paul. Thank you for hosting this. If anyone has questions, catch us at the ABC, shoot us an email.
Yeah.
Happy to chat. Very excited about the rollout of Biocyclone. Thank you.
Congratulations. Great product. It seems to be working great, right? So you've got enough runtime here that it's shown its ability to deal with sand. So congratulations.
Thank you so much. Very excited about it.
Okay, we're a wrap. Thanks, everybody.
Excellent weekend. Bye.